Okay, so these are the components, and whenever your concrete hardens, you have some air voids, and if that air voids are too much, you have a poor quality of concrete. So you have everything. You have solids, liquids, and if you have air voids, you also have gases. Okay, anything that has too much diversity will be chaotic and will not follow any laws, just like our country. Okay, so whenever you have chaos, whenever you have too much diverse elements, you cannot expect any order. And similarly with concrete, you cannot expect to. It's not as predictable as some other metal. Okay, say like steel or aluminum or any metallic structural material. Concrete will not be as obedient as those materials. Okay, so one thing is that whenever there is something which is less predictable, the thing that one person will do is they will assume what the worst case could be. Okay, so for example, if you have unpredictable traffic, you try to leave early. From depending on what your preference is, if you prefer being at home, you try to leave early from work. If you prefer being at work, you try to leave early from home. And how much early do you leave? It depends on the level of uncertainty in it. And this uncertainty is usually can be measured by something known as standard deviation. So what is standard deviation? What is mathematically, how do you describe standard deviation? Simple statistics. How do you find standard deviation generally?
How the distribution is spread. It can be a measure of distribution is spread.
You used what?
Sir, a measure of how much the distribution is spread.
Okay, from on either side of the mean. Okay.
Yes.
So that is standard deviation. And in general, we need to, for concrete, because it is composed of several materials, and you may not exactly have a. If you do so, if you take about concrete technology you have done. If you want to find compressive strength, how many cubes do you test? Compressive strength of concrete. 3. You test 3 cubes, and depending on how much quality was controlled when making those cubes, you may have very close ranges, or you may have a little bit wider range of the compressive strength within those 3 cubes. So depending on the quality control, you say that you may not exactly get the same. For example, you design 25 MPa concrete, but M25 concrete. Okay. So you may not always get 25 for all the 3 cubes. You may get 23, you may get 22, you may get 24. Okay, so you have such uncertainty. So because of that reason, whenever you talk about the strength of concrete, you say that it is a characteristic strength, meaning that it is not exact, but it is a characteristic of that particular mix of concrete. Okay. So the strength one cannot afford to have. I mean, whenever you make design mix, I'm sorry, it's poorly worded, but what I'm trying to say is, when you make a mix of concrete and you want to have a certain strength, so what is that strength that you are expecting that your concrete should not have less than? Okay, so that strength below which your concrete strength should not fall, that strength is known as the characteristic strength. So you just note the way it is defined. It is not defined as the strength of concrete. Okay, it is not defined as the strength of concrete. It is defined as some strength below which that strength of concrete should not fall. Okay, so you're setting a limit and saying that the concrete strength should be above this limit. Okay, so that is known as characteristic strength. So for example, M25 means you should have everything coming above 25, say 25.5, 26, 25.7. It can be, it will be something within above 25. Okay, so that is known as characteristic strength. If you take your code book, I will come to your code book soon. If you take your code book for concrete, it says the strength below which not more than 5% of the specimen results are expected to fall. That is known as characteristic strength. Okay. So then you have something known as mean target strength. So for example, you have done your mix design, right, in your concrete technology?
Yes, sir.
Have you done it? Yes. So you know what is mean target strength, right? I don't need to explain more on this, right? Yes or no? I think you people would be familiar with this, okay, because you've already done design mix design in concrete technology. So I'm not explaining much further what is meant by mean target strength. So basically, what the procedure is, if you want to get a certain strength of concrete, you will actually design your concrete for a greater strength. Okay, for example, one will make the mix proportion for a higher target than what characteristic strength you require. Okay, why do you do it? Because do you remember the formula for getting what is that design strength of concrete? Do you remember the formula for that? There is something.
FCK plus
FCK plus
1.6 into
1.64 sigma. Okay, that 1.64 is your standard. I mean, as a sigma is your standard deviation, and depending on your strength of concrete, you have different values for it. Okay, so this is what a graphical representation of your characteristic strength. So if you test a lot of cubes, and you are actually, if you want to get your characteristic strength to be this much value, 30. Okay. You may have to actually design your mix for 30 plus 1.64 times standard deviation, which will come somewhere over here. And the characteristic strength means, you see that this is 30, less than 5% or below 30. Okay, so that is, so this figure tells what is mean target strength, what is characteristic strength, and how much can actually fall below it. Okay, this is just a simple representation of your thing. Now the next thing is, so in concrete technology, you have entirely dealt with the material aspects of it, and it's just pure concrete. Okay, what pure concrete undergoes and how it behaves. So depending on say when you talk about stress, anything which is given to you will take different types of stresses in different ways. So what are the different types of stresses that you know? Different. What are the different means of stressing?
Compressive.
Tensile, compressive, and then
Torsion.
torsion. Okay, torsion. Then
Shear bending.
shear stress.
Tensile stress.
One more. Yeah, tensile compression over bending stresses, flexural stresses. So concrete will actually behave, will react to these stresses in different ways. Okay. For most items, like for example steel, it will behave the same way whether you test it in compression or whether you test it in tension. As long as tension and compression, they are given by a common name. Do you know what the name is?
Axial stresses.
Axial. So wherever you have axial stresses, metals will usually behave the same as long as it is either tension or compression. When you come to concrete, even within axial stresses, tension, the behavior is different, compression, the behavior is different. Okay. So for example, now this is just a colloquial example. A college student handles exam stresses well, but handles stresses due to his lover or his favorite sports team much worse. Okay, so he will not care much about getting an E or a D, but if he has a breakup or if Barcelona loses, he will not sleep the entire night. Okay, things like that. And an office goer will be very much used to handling stresses from his spouse, but when he goes to work, stresses there will affect him more. So similarly, concrete handles different stresses differently. So all types of compressive stresses, it's good in resisting, and it's an excellent load-bearing material for compressive stresses. For shear, not so good, because whenever you have shear, so if you remember your mechanics of solids, you should remember that whenever you have shear stresses, okay, a pair of shear stresses, you can always actually, using your principal stress concept, you can always be able to identify a principal tension direction and a principal compression direction. Okay, so if you don't remember, just please go back and recollect how shear stresses can be actually transformed to a principal compression and a principal tension direction. So because of that, shear has some, it can be rethought in the form of tension and compression pair. So because there's a tension pair, shear it's not so good. Pure tension really bad. And whenever you have bending, so bending stresses, I mean, you have read bending stresses, right, in mechanics of solids?
Yes, sir.
Okay, what are the two parts of bending stress?
So above the neutral, like based on the bending, one part of one part of the beam will have compression and other part will have tension.
What is that? The point, the location where it changes from compression to tension. What is the location called?
Neutral axis.
The neutral axis. Okay, so in general, if you have a beam like this, below the neutral axis will be tension and above will be compression. So if you have a beam or a flexural member, above the neutral axis, no issue because it's compression and concrete is good in compression. Below the neutral axis, if you just leave it as concrete, it's going to be bad. If you give it rebars, then it will start to be able to actually handle the tensile stresses in beams as well. So this is the basic idea behind reinforced concrete. Okay, so basically when you have beams or any concrete element, you try to actually take care of any occurrence of tension by the provision of steel rebars, because steel is pretty good in taking tension. In fact, much better in taking tension than in taking compression. Okay, so this is the basic idea. So now this is basic RCC design. What do we mean by design? So this is the first thing. So when you do design, you need to first identify the form and the purpose of the finally constructed structure. Okay, so for example, if you are building a simple shed, okay, just a shed, and you're building a column and you're giving the slab. So now for such a case, you don't need to give a very thick or a big column. It's not going to take much load. It's just a covering roof. Nothing is going to be coming on top of the roof except, the weight of the roof itself. Okay, so for that you will probably you may even say that you don't want to use concrete. You may want to just give a wooden pole and keep a sheet over it. Okay, depending on your money, depending on what purpose you're going to use it, you have to decide what the form is going to be and what the use is going to be. Then after that, you will decide what material to use for it. Do you want to use, for example, if it's a truss, you may choose either steel or timber. Okay. If you are going to build the surface for a road bridge, okay, there you will want to use concrete. Okay, you may not want to use that. You may not want to use that. Make a road deck out of wood or out of steel. Okay, it will. If you make steel, will be strong, but it will vibrate a lot. Timber will not be strong enough. Concrete will ensure that neither of that is a problem. So first thing is identifying the structure and the form. The second thing is identify the material after you know what kind of a structure it's going to be. And the next thing is you need to analyze. Once you decide the structure, you want to know what all does that structure experience. Okay, what type of forces? Whether it's going to be subjected to axial forces, whether it's going to be subjected to moments, whether it's going to be also subjected to large levels of shear or low levels of shear. So what are all going to be faced by that structure, you need to identify. And then once you know what are all the things it's going to face, you need to know whether that material is good, how that material behaves in each of these types of forces. So we just saw in the previous slide concrete. It's once you make it RCC, it's going to resist moments pretty well. As far as axial forces is concerned, it's pretty good in compression, pretty bad in tension. So depending on what are the types of forces, you may also try to know how to actually use that material to undergo or take that force. And to do this, you need to have a very good sound knowledge of mechanics. Okay. Okay, because if you want to know axial forces, for example, if you are building a truss, you need to know what is the axial force in each of the members of the truss. For that, you need to know how to analyze. You need to know method of joints or method of sections or Even if you're using a computer, you need to know how to actually use that computer program based on mechanics. Similarly, if you're going to build, if you're getting a bridge girder, it's going to be subjected to bending moments. You need to know how to evaluate that bending moment, how to evaluate that shear force. So only when you are able to evaluate those, you will be able to actually decide how that material is going to behave under those forces. Okay, and so the final thing is you also need to know the relation between the material behavior and the types of stresses. Okay, so how the material behaves and what are the types of stresses that it can withstand. And the final step is based on knowing the forces, based on knowing how the material behaves for those forces. Finally, you can, based on the principles of the established principles, you can decide what the sizes should be, what the proportions should be for the particular structural element. Okay, so for example, you have a bridge, you have girders, you have a deck on top, and then you have girders running this way, you have girders running this way. Then these girders are standing on top of two piers or something like two columns. So you need to know based on the water. So you know that there are going to be vehicles going on top of this. So then the first thing you should need to know is the vehicle which goes on top. How will the slab supposed to be to take that vehicle load? Then from the slab, how will this girder bend? Then you need to know how this girder is going to bend. What are the bending moments in this? What are the shear forces in this? Then from the girder to these piers, what are the bending moments in this piers? What are the axial forces in this piers? How to design them. Then once you know this and once you know the relations, you can decide what you want to do, whether you want to use a RCC beam, whether you want to use a steel beam. And if it's a steel beam, you need to know how wide this should be, how deep this should be, how thick the flanges should be, etc. If it's an RCC beam, you may want to decide how much the dimensions should be for these, what should be the reinforcements, what should be the hoop reinforcements, etc. Okay, so this is the process of design. So identification, then selection of material, then analysis of the structure, behavior realization of the structure, then establishing the relations, then deciding the sizes, proportions, and reinforcement, etc. So this is the process of design. Now coming to concrete as a material under different states of stress. Okay, so this is how concrete behaves under uniaxial compression, meaning that this is your common compressive strength test. Okay, so you have done your like I said, you know how to do a uniaxial compression test in concrete. So what are the ways by which you can, so if you want to do a concrete compression test, what type of specimen do you use? You want to find the compressive strength of concrete. So what type of specimens would you use? What shape?
Cubical or cylindrical?
Cubical or cylindrical. So what sizes are they? If it's a cube, what size? If it's a cylinder, what size?
15 by 15 by 15 and 15 centimeters diameter and 30 centimeters height of cylinder.
That 15 dia and 30 centimeter height. Yeah, either that or you can also use 10 dia and 20 centimeter height also. Basically, the ratio of height and diameter should be 2. Okay, that's the main thing. So this is actually shown for different grades of concrete. It is showing the stress strain curve under uniaxial compression. So you see how this curve looks. Okay, so this is this side is given in Newton per millimeter square. This is in KSI. Okay, Gibbs square inch. So ignore this side. Now look at this side values. Okay, this is about 7.5 m 7.5. This is about m10. This is about m12. No, this is what? m20. This is m7.5 m10. No, this is m15. Sorry, 15 m20 m25 I suppose. M30 or something. It's close to M40. So as you go up, the grade of concrete is different. What is the difference that you note between by going from low grade concrete to high grade concrete? What is the difference in the shape of those curves?
The amount of strain in the steel gets reduced.
The amount of strain in the steel gets reduced, concrete gets reduced. Okay. Rather, you can say the strain at which it breaks is reduced as you go to the higher strength concrete. Okay, so that's fine. That is one thing. How about one more thing? What is common between all these curves?
Stress is proportional to strain.
Stress is proportional to, okay, how proportional in what way? Is it directly proportional or is it
Directly proportional up to the elastic limit.
Okay, directly proportional means it should be strain is equal to some constant times, sorry, stress should be some constant times strain. Is it like that, these curves?
Sir, can you repeat?
Sir, lower.
Right, if you say directly proportional, that means stress equals constant times strain. Do these curves
Sir,
look
this
like
is within the elastic limits. Within the elastic limit, that will be valid.
Oh, okay, fine. Then I have to actually zoom in here. Okay, because the whole curve, does it look? No, are you with confidence able to say that this is elastic? By looking at these curves, does it look to you that they are definitely assuredly elastic?
Plastic. It is in plastic region.
Yeah, I mean there is a certain plastic region, or in other words, you can say that no, what I was expecting is this is not linearly elastic. Okay, it is elastic. Concrete is elastic. It is taken to be concrete is taken to be elastic, but it's strictly speaking, it is not linearly elastic. We assume a linearity for convenience, but it is strictly speaking not linearly elastic. So that is one thing. Something regarding the strain I am asking. Regarding the strain, do you find any commonality between all these curves? Regarding the strain, one particular value of strain.
Sir, at particular value it's reaching maximum.
Huh?
Like at a particular value it's reaching the maximum. Like at
what is that value?
Maximum.
What is that value?
0.002.
0.0. Do you recollect what that value represents from concrete technology? Okay, so
Creep, sir, creep.
What is 0.002 is nothing but it is the ultimate strain of concrete under compression, irrespective of grade. Okay, irrespective of the grade of concrete, the ultimate strain of concrete in axial compression is 0.002. Okay, similarly saying, so other thing that you can find is these. If you look at these two curves, they are actually ending at something after 0.003. Okay, so this picture is taken from the ACI curve. ACI. This is the American standard. Okay, this curves. So there they use ultimate failure strain in flexural tension to be flexural compression to be 0.003. In IS 456 we use 0.0035. Okay, which is the ultimate failure strain in flexural compression. Okay, so there's a difference between the strain which you consider for axial compression and what you consider for flexural compression. Okay, the reason for that will come later. So that is this point where you say that the ultimate failure strain of concrete in flexural compression is 0.0035. Of course, these low grade concretes do not end at 0.0035, but we do not use the strain beyond that. We make a common strain for this flexural compression. So this curves, these are the conditions for getting these curves. It should be loaded at a strain rate of 0.001 per minute. Okay, 0.02 is the limiting strain of axial compression, and the reason being you cannot increase the stress beyond this. because this 0.002 strain is the location where the stress has reached the maximum. So if you try to increase the strain, the stress is only going to reduce. 0.0035 we used as the limiting strain for flexural compression. The reason will be told later. Now actually cube strength versus cylindrical strength. Some testing standards suggest the ASTM. Okay, ASTM means it is for what is that ASTM? American standard for testing in materials, I suppose. Okay, it's known as ASTM. It uses cylinder test to determine the strength of concrete. I already asked you. You told me the height by diameter should be 2. The Indian standard uses standard cubes. You already told me the size is 15 cm cube for determining the character strength. Of course, there should be a relation between both of them. Okay, so one thing is when you test a cylinder like this, so you have, I mean, this is height, this is diameter. The ratio is 2. You have already told me that. So the distance from the place where you if you look at this is where the load is applied. Okay, the top surface of your cylinder, that's where the load is applied. If you look at the stresses at this top surface, you will find that at the circumference you will have very low stress. As you go near the center of the cylinder, you will have highest stress. But if you go into the cylinder rather, if you go into the cylinder for a distance greater than 3 times the diameter, okay. Of course, we are not going to reach 3 times diameter. We are going to reach only 2 times diameter in your cylinder size. The ratio is 2, no? So only if you have a distance between loading point to the location to be greater than the 3 times of diameter, you will have a uniform stress distribution. But our cylinders, they are of a ratio 2, not 3. Okay, so therefore, even at the center of the cylinder, you will not have uniform stress distribution. It will be a little bit ununiform. Okay, so that is one thing. And other things, when you press it, the cylinder will try to expand in its middle. It will try to expand in its middle. However, at the top, because you have this plate on top, you have the plate on bottom. At that particular location, because there's a friction between the plate and the surface of the cylinder, it cannot expand that much. Okay, because there's a friction force which will oppose this expansion. So that is known as Platen effect. This is known as Saint-Venant effect, where if you go greater than 3 times of the diameter, only you will have uniform stress distribution. So neither this is the case, and also you have this friction. So because of that, cylinder strength will actually be lesser than your cube strength, and it is about 0.8 times of your cube strength. So FCK is the characteristic cube strength. FC is the cylindrical strength. Then FC is only 0.8 times of FCK, and in general, the actual strength of concrete will be taken to be the cylindrical strength. Okay, so in general, for design purposes, the more closer strength to the truth is your cylindrical strength. So another thing is you're looking at is the loading rate. So as you see, if you keep increasing the rate of loading, you have a difference in your strain as it goes over time. So of course, the maximum strain will not be much different. It's maximum stress rather. So this is the ratio of concrete stress to the strength. Okay, so if you load it really fast, you get a high strength, but it comes down soon. If you load it really slow, look at this rate, 0.001 strain per 100 days. Okay, such a slow loading rate. If you do it, you see that your strength will be slightly lesser, but the strain really it does not come down very soon. But the one that we use in general for testing is when you do a test, we cannot load at even this rate. Okay, it's going to take time forever even if you load it at 0.001 per hour. Okay, so this is the standard, the bottom curve. This is the standard testing curve which you will get if you actually test it. So normal service conditions correspond to low strain rates, meaning that if you're going to the lab and testing, okay, I'll give you two situations. One is you are testing in the lab. Okay, you are probably doing this test. Okay, you're doing this test in a lab. Okay, that is one situation. Another situation, you're building a big structure and you're keeping some strain sensors on it, and you're going to measure the strain for the whole year. Okay. So which curve will you get if you test in the lab? Which curve will you get if you test the building? You have some curves over here. Which strain curve corresponds to lab test? Which strain curve corresponds to actually putting sensors in a building and measuring it over time?
The topmost curve for building.
Topmost curve for the building, and for the lab?
The bottom one maybe.
Yeah, mostly the bottommost curve. Sometimes they'll use the second curve, but it's only for specific tests. Most common is the bottommost curve. Okay. So that's why I meant normal service condition means in actual application, like in a building. So in a normal service condition, like in a building, it will correspond to low strain rates like this. Okay, so you get the gradual yielding curve. So of course, you see, after this 50% of strength, see, at least till this 50% of strength, you can have almost a straight line. It's almost a straight line from stress to strength ratio of 50%. Beyond 50%, it starts to become a bit parabolic. Okay. So this portion of the curve should be idealized by a curve as described in the equation given by this. Okay. So until this point, about say over here, it can be taken as an almost linear thing. Beyond this part, it becomes a bit parabolic. Okay. So you need to have a equation for that. This is the commonly known equation for that, given as FC equals FC double dash. EC is your compressive strain for that 0.002. No, sorry, no. EC is the current point strain, epsilon C. Epsilon naught is that 0.002 you see over here. This is epsilon naught. Okay, and this is FC double dash, which is the top peak strength of concrete, ultimate strength of concrete. So based on that, we'll be able to model this parabola. Okay, so this is the ACA code, and there's a similar equation suggested also in your. This is the number of your code book for reinforced concrete design, plain and reinforced concrete design. So I hope you have come across this code before. Yes.
Yes, sir.
Yes or no? You have come across this, right?
Yes, sir.
Okay, good. And one is direct axial strain. You also can have lateral strain, meaning that. So this direction strain is axial strain. When you have expansion this way, it becomes lateral strain. Okay, this is more detectable in your cylinder tests where the diameter will expand a bit. For uniaxial compression, there is lateral expansion. For example, in a cylinder, you will have the increase in diameter while you compress this cylinder. So this is known as Poisson effect. Okay. So then you have this figure. Longitudinal means axial, along the length. Okay, this is axial. Lateral or transverse both mean the same. So that is this strain curve. Okay. So note that for higher longitudinal strains, for example, 10 power minus 4 and 12 into 10 power minus 4. Where is it? Here. Okay. Okay. 10 into 10 power minus 4 and 12 into 10 power minus 4. Lateral strain is about only 2 and 3. Okay. So that is the ratio of transverse strain to longitudinal strain. So what is the other name for ratio of lateral strain by longitudinal strain? What is the name of that? It's known as Poisson's ratio. So you can just take this ratio. You see that the Poisson ratio of concrete can be taken about 0.2 by 0.3. Simply know this. You take about 10 divided by 2 divided by 10 or 3 divided by 10 like that. So that's what this is. So these are the different tests and the different code books. Cylindrical strength, you can use IS 516. Similarly for cube strength as well. I hope this code books also you have heard in concrete technology, IS 516.
No, sir.
Or not heard. Okay, this is the code book which tells you how to do these tests. Okay. So you can just have a look at this code books. It's freely available on the internet. So your task for today is just probably go to the internet, search for IS 516 and just go through what they say for these two tests. Okay. You've already learned this test, but just at least open the code book and see that there is a code book for these things. If you want to find the modulus and Poisson's ratio, I mean, IS 516 does not have specified a test. You may have to use the ASTM standard. Split cylinder strength, IS 5816. Split cylinder strength is usually this test and this test, both of them. Split cylinder tensile strength and a 3-point bending test given by IS 516. These two tests are used to find the tensile strength of concrete. Now, why do you think we are not doing see, for example, compression strength, we are taking a cylinder strength and compressing it and finding the compressive strength. Similarly, if you want to find the tensile strength of a steel rod, if you want to find the tensile strength of a steel rod, what test do you do? And what machine do you do? I'm not sure if you people would be aware of it because you people have all done online lab. But anyway, still I'm asking.
UTM maybe.
UTM.
Universal Testing Machine.
Okay, so why don't we do the same thing for concrete to find the tensile strength? Can you do it? Actually, can be done, but nobody prefers it. Why?
Because there is no buckling involved.
So there is disturbance on your side. Why don't somebody do a UTM test for finding the tensile strength of concrete?
Concrete is weak in taking tension. It is best in taking compression loads.
It's weak in tension, and other thing is other thing is you cannot actually very easily grip concrete on a UTM. So these two reasons. So if you directly measure the tensile strength, you will get a very low value. It will just fracture at wherever you're loading it. Okay, so it will be very sudden and immediate, and you won't get a proper failure pattern. So instead of that, you do indirect tests. Okay, so when you press it, when you put a cylinder ulta, make it lie on its side, and then you compress it. This is when you look at this. Again, this compression. It's a compression testing machine. It's still compressing it. Then why do we call it as a tensile strength test? It's actually doing compression. Then why is it named as cylinder tensile strength test? Any guesses why? How can that be called as tensile strength test if it's being compressed?
Maybe from the Poisson's ratio.
So on the other axis, it's being
Poisson ratio, rather when you compress it this way, it gets tension on the other side, okay, the lateral side. So that's how it becomes a tensile strength test. So this, so there's a calculation or conversion between the compressive load at which this crack occurred and the tensile strength. So that will be given in this code book. You can have a look at it if you want. Similarly, when you have bending, okay. So as you know, bending top is compression, bottom is tension, and based on this tension happening at the bottom, you can actually also evaluate the tensile strength. Of course, you can also have slightly more complex case, which is biaxial loading, meaning that for a cube, instead of just compressing it in one direction, stress another direction as well. Okay, so here these two axes are telling you Fu is your strength. F2 is the stress which is applied in this direction. F1 is the stress which is applied in this direction. So you have a quadrant. So the upward and rightward axis are tensile F1 and F2. Upward meaning this is a tensile direction. This is also a tensile direction. Right. So this is the origin. If you go right, it is a tensile F2. If you go up, it's a tensile F1. Similarly, you come down, it's compressive F1, and you go to the left, it's compressive F2. So this quadrant, okay, this quadrant that you see over here, it's marking the envelope of the stresses when both F1 and F2 are compressive. Okay, when both F1 and F2 are compressive, you see that your concrete can actually reach a strength which is greater than the uniaxial compressive strength. Fu is your uniaxial compressive strength, meaning that this test which you did over here, you may have got some strength. Okay, say M25 and you got 25 as a strength, 25 MPa as a strength. If you actually do a biaxial compression like this, then the strength which you actually will get will not be 25, it will be 25 times 1.2. So when you do a biaxial loading, the strength has increased. This seems a bit strange. Okay, so just you're loading only one direction, strength is some value. Now you're adding additional load in another direction. But strength instead of reducing is increasing. Why?
Sir, the loading is contributing to the strength, sir.
Huh?
Actually, the concrete specimen will have a failure if we have in one direction. Like if we are providing, like in the lateral direction, it will have a failure. If we provide it, like if we restrain it from the lateral direction, then the strength will increase automatically.
Tell it again.
It may get amplified, sir.
Huh? No, come and tell some. To the person who replied first time, just tell your answer again.
Sir, when we are compressing the specimen in uniaxial direction, like the concrete specimen may get a failure in lateral direction. So when we are restraining the concrete specimen in the other, like the lateral direction, in biaxial loading, like we can increase the strength.
Okay, fine. Okay. Okay, you didn't tell it exactly, but I get your idea. See, basically what he's saying is, when you compress it in this vertical direction, the lateral direction will, basically the lateral direction will be unrestrained when you don't apply a load in the lateral direction. Okay, so there is a possibility that, in fact, if you imagine the cylinder, it's going to expand and it's going to have failure. Now, when you apply a compressive direction, compressive load in this lateral direction, it is going to restrain and it's going to prevent the lateral direction from expanding or from failing. It's going to press it back inside. Okay, so the cube is there. It's trying when it's being compressed, it's trying to expand a bit. If you apply a compressive load in this direction, it's going to again push it back inside. Okay, it is countering your failure. So that is why your load, the apparent load the strength which you get will be higher if you do a biaxial compression test. However, if one of those directions is tensile, then it becomes really bad. Okay, so you get only you get less than 0.2%. You get less than 20% of the strength which you get by a uniaxial test. If for example, if this F2 becomes tensile, then already the side is expanding. You pull it further, it's going to fail much faster. Okay, so that is what is happening. So, what is this picture? You see some circles. What circles are they?
No circle.
There?
More.
No circles. What do more circles tell you?
Geometrical interpretation between the shear stress and normal stress.
Okay. So that's what this is also telling you. When you if you have uniaxial compressive strength, you look at the size of the circle. In uniaxial compressive strength, you have such a large circle, meaning that your failure envelope is quite big. And when you have a very general state of stress, it's going to be a normal circle. Okay, and if you have uniaxial tensile strength, it becomes like this. Okay, so this is just to tell you how these stresses are related. Probably this is how much more do I have? Just a minute. Okay, I think you can finish it off. So you know what is creep and shrinkage rate? Creep and shrinkage you have heard right already previously in concrete technology. Okay, so I don't need to explain much of it. Basically, creep is just it's a strain which takes place over a long time and which under constant load. So that is known as creep. It depends on several things like all these things. Time under the load, age when it's loaded, relative humidity, thickness, slump, percentage of the fines, air content. It depends on all these things. And shrinkage, it happens because of your water cement ratio. And in order to control it, you do sufficient curing. And the final part of reinforced concrete is your steel bars. Okay, and this is the stress strain curve of, this is mild steel, this is high strength steel. Okay, so just like your concrete, which is when you have low strength, strength will be low, the strain and ductility will be quite large. When strength is more, your strength will be more, but your ductility or strain will be much lesser. Okay, so this is typical for also for steel. This is mild bars. The top one is HYSD, cold twisted bars. Okay, this is the one which is more commonly used for reinforcement. The plain bars are used mainly for purposes like tying your reinforcement and other things. Okay, so you'll know what is tying later when you start doing beam design. So point A is known as your yield stress. You know that. EAB, this region AB is known as your yield plateau. C is the ultimate stress. It's the highest point of your stress. D, where the steel rod breaks, is known as your breaking stress, and from C to D, where the stress is slightly reducing, is known as the softening range. Okay, so for high strength yield deformed bars, you may not have a sharp yield point. Okay, so you use something known as a proof stress, which is obtained by drawing a line at 0.002% strain and making it to touch the curve. Have you heard of proof stress before in your mechanics of solids? Okay, this is what is proof stress. So sometimes what will happen is your stress strain curve will not be having a sharp yield point. This is especially true if you have high strength steel bars. You may not have a very sharp yield point. So in that case, you want to know how to find the yield strength. At least here, you know, this is a very sharp point. This is yield stress. If it's a curve like this, then you won't know what. If the curve is like this, you won't know what is the yield stress. So in that case, what you do is you just mark the point of 0.002% of strain. Okay, 0.002 strain. You just mark the point, draw a line parallel to this initial line, and then make it touch the curve. Where it touches the curve becomes your proof stress. This is the way to find yield for high strength bars. This is just a broken rebar. So it can be used as reinforcement. It can be used as confinement as well. So you see several bars over here in the column. They are main bars. These circular hoops are known as confinement. And usually the RCC columns, you can just see over here. If it does not have confinement, this is how it behaves. Once it is given confinement, you can see how the strength also increases and it also takes a bit of ductility. Okay. So this is plain column without no confinement, and the dotted lines are all with confinement. You can see the advantage that you get by giving confinement. Okay, so why does this confinement increase the strength? Because once again, the same cylinder, you just assume you have a plain cylinder, it will expand. Okay, if you give it confinement in the form of circular hoops, okay, it's very easy to expand concrete when you press it. When you give it a hoop, steel hoop inside, that hoop has to expand, and making that hoop to expand is not as easy as making the concrete to expand. So therefore, it will actually take a lot of stress and prevent this expansion from happening. That is known as confinement. The lateral expansion causes the steel hoops to experience hoop tension. Have you heard of hoop stresses? Advanced, see, in your mechanics of solids. Have you heard of what is hoop stress? Cylinders.
Yield stress.
You heard it, right? So it will develop a hoop stress because steel is strong in tension, it will not fracture easily. It will not actually expand easily either. So thereby the hoops will confine in the concrete, meaning that they will keep the concrete inside without allowing the concrete to expand or anything else. So with this I'll stop today, and tomorrow we'll go into design philosophies.